AOSP mining, extraction, and upgrading process is unique and complex, and this is how it actually works. Before the oil sands can be mined, the layers of muskeg rock and soil known as overburden are cleared away and stored for later reclamation use. Giant shovels measuring 7 stories each, with a large bucket that scoops up to 100 metric tons of oil-soaked dirt in a single load, pick up the oil sands ore and drop it into a series of gigantic heavy hauler trucks. Each 400-ton truck carries enough bitumen to make about 200 barrels of oil and can make 30 to 50 trips each shift. The trucks dump the oil sands into 2 massive primary crushers. Inside the crushers, huge steel teeth break up and grind the large chunks of ore down to about 16 inches or 45 centimeters. Each double-roll crusher can process 14,000 tons of oil sands ore per hour. The ore is then carried along the world's largest capacity conveyor belt to a storage silo. There, ore is fed up 3 conveyors to the rotary drum breakers, where warm water is added and the rotating drums agitated vigorously, creating a mixture called slurry. The slurry is then moved through a 2-kilometer pipeline to the extraction plant, a process known as hydrotransport. The slurry sloshes along inside the pipeline, and the movement further agitates the bitumen, beginning the separation process. After hydrotransport, the slurry enters the primary separation cell, the first stage of bitumen extraction. The cells stand out as large cones against the backdrop of the buildings and pipe racks of the plant. When the slurry enters the separation cells, water is added to help separate out the bitumen. In the cell, the bitumen floats to the top of the vessel, the sand sinks to the bottom, and a combination of mostly water mixed with sand, bitumen, and clay sits in the middle. These are known as middlings, which are treated again to recover more bitumen. The product from extraction is known as froth and typically consists of 60% bitumen, 30% water, and 10% solids. In the froth treatment plant, the froth is mixed with a paraffinic solvent that reduces viscosity and precipitates asphaltenes. The result is a water and solids-free bitumen, clean enough to be upgraded using hydrogen addition technology. This mixture of bitumen and paraffinic solvent, or diluent, is called dilbit. The dilbit is shipped 493 kilometers south to the Scotford upgrader through the corridor pipeline. Light oils that are part of the bitumen received from the mine are first separated, including the diluent that is used to transport the bitumen to the upgrader. The remaining residue, a tar-like fluid from the bitumen, is upgraded by applying heat, hydrogen, and pressure to break the large carbon chains that make up a bitumen molecule. Upgrading methods create lighter hydrocarbon molecules by either removing carbon or adding hydrogen molecules to the long bitumen molecule chain. Shell uses the hydrogen addition process. In a vessel called a hydrocracker, hydrogen is added to create smaller hydrocarbon molecules that are easier for refineries to process. Most of the hydrogen used for hydrocracking is produced on-site by a hydrogen manufacturing unit. The byproduct created is then converted to pure sulfur in the sulfur recovery unit. The hydrogen addition process has some advantages over the traditional coking process used at other oil sand operations. Coking removes carbon, creating a waste byproduct.